Chapter 5, Introduction to Solutions and Aqueous Reactions. Science may be described as the art of systemic oversimplification, the art of discerning what we may, with advantage, omit, which is something that we frequently do in general chemistry. I don't know who Karl Popper is, but I'm sure Wikipedia does. Okay, so when we're talking about solutions, we're not talking about answers. We're talking about things dissolved in other things. So a lot of chemical reactions involve reactants dissolved in water or other liquids, but usually water. These are very common and also important reactions. A homogeneous mixture of two substances, it has to be homogeneous mixture of two substances, is called a solution. It does not necessarily have to be a solid in a liquid. It can also be a liquid in a liquid. It could be a gas in a gas. It could be a solid in a solid. It could be a gas in a solid. Any of the states, basically, that you can think of, you can make a solution with those two states. Our formal definitions for the two things or more that are in a homogeneous mixture of two substances or more, a solution, our formal definitions are that the solvent is present in the greater amount. Solvent is the majority component. Most of the thing is the solvent. And our solute is a minority component or the minority component. These definitions are more relevant when we're talking about a liquid dissolved in a liquid or a solid dissolved in a solid or something like that. You can have more than one solute in a solution, and the amount of the solute is also variable. When we're talking about aqueous solutions, aqueous just means water. So it's a solution where water is the solvent. And aqueous solutions are very common. We saw them in our chemical reactions last class with the AQ inside of the parentheses. That's talking about aqueous reactions. So we've got whatever our compound is, oftentimes it was a solid, and it's dissolved into water. Along with this, we have varying levels of solute. We've got a couple types of levels. When we describe things qualitatively, where we're not putting numbers to it, we're just like using words to describe it, we've got dilute solutions. Dilute solutions have small amount of solute. Dilute or not strong or weak solutions, depending on the context. So there's only a small amount. A dilute solution of salt in water wouldn't taste particularly salty. Concentrated solutions have a large amount. So these would be strong solutions, is another way that we would refer to them. So we've got a lot of the solute in the solution compared to the solvent. So a small amount of solute is dilute, a large amount of solute is concentrated. We can also quantitatively express solution concentration. We'll often do this with molarity. Meet your new best friend, molarity. Molarity has a symbol capital M, which is important. So molarity is the amount of solute in moles divided by the volume of solution in liters. So solution meaning solute or solutes plus solvent. So the whole thing mixed together, that's the solution in liters. So molarity is amount of solute in moles over the volume of solution in liters. Or another way that you could write it, big M equals moles over liters. And a cool thing that you can do, what I usually do when we're doing problems that have molarity in them, is you can take capital M and turn it into moles per liter. You can just swap these units for each other. So I usually talk about molarity as it being secretly multiple units. It's technically just one unit, it's molarity. But because we can turn it into moles over liters, it's secretly more than one unit. All right, if we want to make a solution of a specified concentration, here's the correct way to do it. Or here's a correct way to do it. So let's say we want to make a specified solution of sodium chloride. We are going to have a volumetric flask. This is a 1 liter volumetric flask. Volumetric flasks are good for measuring exactly one volume, and they're only good at measuring that volume. If you want to measure any other volume, grab a different volumetric flask or use some other piece of glassware. So this volumetric flask has a mark on the neck, and that mark, when the meniscus of the water is at that mark, it's 1 liter, and it's usually plus or minus a really small amount. So it's a very precise way of measuring exactly that one amount. So the first thing that we would do, we're making a salt solution. We're going to add our 1 mole of sodium chloride to our flask. We're going to then fill it up part way. You want to fill it up before it gets to the neck of the flask, because once it gets to the neck of the flask, it does not stir well. It does not shake well. And so you would fill it up part way, swirl it around until it's all completely dissolved, and then finally, very carefully, fill it up right to the line on the neck. If you fill it up over the line, you get to remake it. If you fill it up under the line, just add a little bit more. But if you fill it up too much, it's no longer 1 liter, and you might have to remake it depending on how particular you are about the solution. So one of the important parts about this is add liquid at the end. If you filled it up to 1 liter and you were somehow able to magically stir it really well, if you fill it up to 1 liter with water and then you add the salt in afterward, the salt takes up space, and so your water level is going to go up, and now you're no longer the concentration that you wanted to. So you'd want to add your solid first and then fill it up to the correct amount. Let's say that we want to make a solution. We want 3 liters of a 2 molar solution. How many moles of solute do we need to do this? We're looking for moles of solute for 3 liters in 2 molar solution. So we're going to use our equation for molarity. Big M equals moles over liters. We have liters, we have molarity, we are looking for moles. So we can rearrange. So big M equals moles over liters. We move liters, and we're left with moles equals molarity times liters. So we plug in our numbers. Our molarity is 2.0, capital M. Our liters is 3.0 liters. So our answer would be 6.0 moles of solute. That's one of the ways that you can solve the problem. Another way that you could solve the problem is turn the molarity into moles over liters. Now we've got starting things of 3.0 liters. We've got 2.0 moles over liters. If we wanted to get the moles out, you multiply the liters by the moles over liters, so the liters cancel and you're left with moles. That's the way that I usually like to solve these problems when I'm doing it by myself. I understand that's a little confusing for some people. Molarity is also a place where we can use a little triangle method. I believe that I told us about this with density. So molarity equals moles over liters. If we force this into a little triangle thing that looks like this, getting a potential spam phone call, we decline those. So if we force it into a little triangle like this, the thing that we're looking for, we cover up. So we're looking for moles of solute, cover up the moles of solute, ignore that. Look at the other two things and how they are related. So molarity times liters, they're next to each other, that will give us moles. So the little triangle method thing also works for this equation, if you'd prefer to do things that way. Oftentimes, calculating solution concentration will require a grams to moles calculation, since we don't just magically know moles most of the time. So for example, we want to calculate the molarity of a solution. It's made by adding 45.4 grams of sodium nitrate to a flask, and then dissolving it to create a total volume of 2.50 liters. So our goal is finding molarity. We can get to molarity with our molarity equals moles over liters. So we would need to have moles and liters. Do we have moles and liters? We don't have moles and liters. We've got liters. To get to the moles, we'd have to convert our grams to moles. So we're going to need the molar mass of sodium nitrate. Where did I put my calculator? There it is. Okay, so 1 sodium, 22.99, 1 nitrogen, 14.007, and 3 oxygens at 15.999 apiece. We've got 84.994 grams per mole. So starting with our 45.4 grams sodium nitrate, we divide by our molar mass, and we'll get the number of moles that we have, 0.534 ... Remember, the ... means there's more things and we're using them. We're not just saving ourselves time and space, we are also still using those numbers. Okay, so now we've got moles and we've got liters, so we can solve for our molarity. We take our moles of solute, divide by our total volume of solution, and our molarity is 0.214 capital M NaNO3. Questions? The way that we would typically pronounce this, the capital M, is molar. So it's 0.214 molar sodium nitrate solution. So just drop the itty at the end. Question?
So let's say there's two solutes, so basically, just depending on the solute you're looking at, just wanna...
So if you have multiple solutes, you can calculate the molar concentration for each of the solutes individually. They would all still have the same volume, but the number of moles of each would differ, if that's what you were going for. Cool. Okay, other places that we can use molarity. So you can use molarity as a conversion factor. This is why I often like to convert that capital M into moles over liters. So take that 0.500 molar and make it moles over liters. So we can use that to convert liters of solution to moles. We could divide by it to convert from moles to liters of solution. This lets us do a dimensional analysis approach, so thinking about what are the units, how do we cancel units to get the units we want. That's what swapping out molarity for moles over liters is really helpful for. You can always use the equation approach, and that's valid too. This is just a little faster, I think. So another way that we can use this, how many grams of sucrose are in 1.55 liters of that concentration molar sucrose solution? So we are given some information. We've got liters, we've got molarity, we're looking for grams of sucrose, and we're given a chemical equation for sucrose. The place that I would start this equation, or start this calculation, is with liters. 1.55 liters, because molarity is secretly moles over liters. And since it's moles over liters, we can multiply our liters and our moles over liters. So that would look like this. 0.758 moles is moles of sucrose over 1 liter. I usually leave off the 1. So this converts from liters to moles, and now we know how many moles are contained in that amount of solution. So we've got 1.1749 moles sucrose. Can we go from moles of sucrose to grams of sucrose? We sure can. What do we need to do that? Molar mass. So we'll have to calculate a molar mass for sucrose. So our molar mass of sucrose for carbon, we've got 12 with about 12 grams per each. We've got 22 hydrogens, about 1 gram per mole each. And we've got oxygen, 11 of those, with just shy of 16 grams per mole each. Sum those up. Boop. We get 342.297 grams per mole. The grams is on top in the molar mass, so we're going to multiply our moles by our grams per mole. So that our moles cancel. Moles cancel. And we've got 402 grams sucrose. Which is a lot of sugar. It's almost a pound of sugar. Questions about doing that calculation? All right, if we dissolve 25 grams of salts in 251 grams of water, what is the mass of the resulting solution? Think about it. Pick an answer. What do we think? We've got a guess for B. We've got a guess for A. When we dissolve the salt into the water, does the salt still exist? Yes, it still exists. It's changed form. It still exists. We just add the masses up. Maybe I was just misreading the A. Maybe I'm bad at reading lips. That's true, but maybe it's also true in this situation. So the correct answer here is B. The salt still exists. It's got a mass of 25 grams. The water also still exists, 251 grams. We haven't destroyed anything. We did rip apart our salt molecules, but they still exist. Another thing we often do with solutions is dilute them. The reason that we dilute solutions is because if you want to make a really dilute concentration of a solution, it often requires either really, really small amounts of our solute or really, really large amounts of our solution. And that can be really impractical. So it can be helpful to do a series of dilutions to get down to those lower concentrations. Also, it's convenient to store things in really high concentration solutions called stock solutions. So if you were to go back into our stock room, the stock solutions are the solutions that we would have in stock. They tend to be more concentrated solutions. Oftentimes they are concentrated, meaning they're the highest amount that you can get, or they're close to it, stock solutions. And that makes it easy to make lower concentrations of solutions. Just add solvent, oftentimes water. So adding solvent, really easy. If you've ever tried to remove water from something, like, oops, I mixed my drink wrong, let me remove one of those water components. It's very difficult, obscenely so, unnecessarily so. So it's really hard to move from low concentration to high concentration. It's much more space saving to start with a high concentration solution. So we've got this equation that is good for solution dilution, and that's the only thing that it's good for. This one, this M1V1 equals M2V2. Don't use this for anything other than diluting. Only good for diluting. That's all it's good for. That's the only thing that you should ever use M1V1 equals M2V2 for. The reason that this works, M1 is the same as moles over liters in one state. And we're multiplying that by V1, which is an amount of liters. Right? So we're saying in one concentration of solution with one amount of solution, we've got a certain number of moles. Then we're going to add solvent to that. Adding solvent doesn't change the amount of solute that we have. So this moles amount is going to stay the same. All we're saying with this equation is the amount of moles of solute that we had at the start is the same amount of moles as we had at the end. It's just a little bit more spread out. These calculations tend to be really easy. The most important part is that you don't get states 1 and 2 mixed up. So make sure that you know which molarity goes with which volume, and you should be fine. And don't use it for anything other than diluting, or it's wrong. Even if it's not technically wrong, if it's a short answer and you use this and it's not a dilution question, I'll mark it wrong. It's one of those things that I'm weird about. All right, let's say that we want to prepare 3 liters of 0.500 molar calcium chloride from a 10 molar stock solution. The stock solution, we can't really change the concentration of that, but we can do a calculation, figure out how much of that 10 molar stock solution we need. And I don't remember if this is a slide. It's not a slide. So we would do our M1 equals M2V2 calculation down below. So this 3 liters and that 0.5 molar, this is what we're putting in as V2 and M2. This 10 molar is our M1. So the problem that we would be solving to figure out how to do this dilution is find V1. How much of the stock solution are we using? So how much stock solution are we putting into our 3-liter volumetric flask and then filling it up to 3 liters? So we do that calculation. Down here, it turns out it's 0.150 liters. So we'd pour that amount of stock solution into our big flask. Then we would fill it up to the 3-liter mark. And boom, we've got our solution. So it makes it really easy to prepare pretty much any volume, any concentration of solution as long as it's below that stock solution concentration. especially once you practice it, once you get good at it. Okay, one for you to try. To what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? Okay, what's some information that we are given? We're given 100 milliliters, 5 molar calcium chloride, 0.750 molar calcium chloride. What are we finding? We're finding volume in milliliters. And we know that we're finding volume in milliliters because it's next to our question word, what? So sometimes it's helpful to rewrite all of the information that we're given just so we can start to make sense of it. So we've got a volume. That volume, I'm going to write in the middle. Our volume is 100.0 mLs. We are also given some molarities. The molarities are 5.00 molar CaCl2 and 0.750 molar CaCl2. This volume gets paired with one of these molarities. Which one does it get paired with? Does it go with the 5 or the 0.75? It goes with the 5. So these are right next to each other. So 100 milliliters of a 5 molar calcium chloride solutions. So it doesn't matter if you label that state 1 or state 2. All that matters is that they get the same label. As long as those get the same label, you'll end up with the correct M1V1 equals M2V2. That means that this M2, in this case, the way that I've labeled them, would be M2. And what we're looking for is the volume that goes along with that, which is V2. The most important part, the place where you're most likely to mess up, is just getting your 1s and 2s mixed up. Okay, so M1 V1 equals M2 V2. We are looking for what we've labeled in this case V2. So we divide both sides by M2, flip the left and right, V2 equals M1 V1 over M2. If you solved for V1, you'd get the same thing, but the labels would be switched. That's why it doesn't matter if you label them 1 or 2. Okay, so V2, we're going to put M1 and V1 on top. M1 is 5.00 molar, moles over liters. CaCl2, so I'm swapping in moles over liters for the molarity, times V1, which is 100 milliliters. Got to include that 0.0. So the liters parts would cancel there. And we're dividing this by 0.750, which is also moles over liters. And the way that this works out is the moles would cancel, the liters would get flipped to the top, and this ends up with units of milliliters CaCl2. You can always, if you want to, get rid of metric prefixes, and then if you need to, bring them back later. That's always an option. It's the safe way to do things. But for this problem, we were given a volume in milliliters, and we were finding a volume in milliliters. We didn't need to do that. So we'd plug in 5 times 100 divided by 0.75. And the volume that we need to dilute this to is 667 after rounding milliliters. 2/3 of a liter. Questions? Cool. We just learned about stoichiometry. We can also do it with solutions. So with solution stoichiometry, we are typically going to be given a volume instead of a mass. And we will often also be ending in volume, or we might end in molarity, also instead of mass. And what we're using instead of molar mass for our first conversion factor is molarity. So in some ways, solution stoichiometry can be easier because we don't have to find a molar mass. We could also change up the solution map for this. We could start with mass and go to moles to volume or to molarity. We can also do that. So there's like a lot of parts that we can change. Integral part, the part that's not going to change, is that we've got stoichiometry in the middle. So we're still going to be using a balanced chemical equation, but we can change how we start the problem and how we end the problem. So our ratio from the balanced chemical equation, still doing that stoichiometry part for us. So an example of this. We've got a bunch of words given to us. We've also got a chemical equation given to us. Is the chemical equation balanced? Probably, because we've got coefficients, right? We've got coefficients, it's probably balanced, so we don't have to balance it ourselves. That's great. What volume of a given information, 0.15 molar HNO3 solution will completely react with 35.7 milliliters of a concentration sodium carbonate solution, according to the following balanced chemical equation? What are we finding? We're finding volume in milliliters HNO3. So we are looking for, at the end, mLs HNO3 nitric acid. And again, we want to make sure that we don't get our numbers mixed up. The 35.7 milliliters is paired with the 0.108 molar sodium carbonate solution. What are the two chemicals we care about for this reaction? Yeah, we care about HNO3 because that's what we're going to be going to at the end, what we're finding. And we care about Na2CO3. So for our ratio step, our stoichiometry step, those are the two things we care about. We can ignore everything else in the equation. Ignore it. Get rid of it. We don't need it for this particular problem. Okay, so we need to get to milliliters HNO3. We can get to volume of nitric acid. We need something that relates volume and something else. Any ideas? What could we use to get to liters or milliliters? Moles. We could use moles. We would need molarity. We have molarity, very convenient. And this would be moles HNO3. To get to moles HNO3, we could get there from milliliters. We don't have milliliters because that's what we're finding. So we'd have to change something else. We'd have to change our chemical. So we could get there from moles Na2CO3. Can we find the moles of Na2CO3? We better. we can find it with milliliters and molarity of Na2CO3. So milliliters or liters, depending on which one you want to start with. Na2CO3. So we're doing mils to moles to moles to mils. Again, we can get rid of the mils part, the milli prefix. I'll do that for this one, just so that we see how that works. But because we are starting with milliliters and ending with milliliters, we don't actually have to do that. We can just leave the milli part on throughout the whole thing. Always safer to get rid of it, though. So let's see what this looks like. We're going to be starting with 35.7 milliliters. The reason we're starting with milliliters instead of molarity is secretly 2 units. I like to start with 1 unit, the simpler units. To turn this into liters, we divide by 1,000. There are 1,000 milliliters in 1 liter, or 1 milliliter is equal to 1,000th of a liter. So 0.0357 liters. Now we've got liters. We've got molarity. The molarity that we are given is 0.108. Scooch this over. 0.108 molar. Remember that molar is moles over liters. So looking at the fact that it's moles over liters, we can just multiply by the liters. The liters times the molarity will give us moles. So liters cancel, and I forgot to have my chemical unit in there. So the amount of moles of sodium carbonate that we have is this many. So we've got that many moles of sodium carbonate, Na2CO3. Since we've got a balanced chemical equation, we can figure out how many nitric acids we would have had to react with our Na2CO3. The red underline here for completely react, that just means that all that is that's telling us we can use our stoichiometry ratio. We're going to completely use one up, because if we don't say that, then somebody might be like, actually it didn't say that we completely react it, maybe it only partially. So we're avoiding all that nonsense by saying completely react with. All it lets us do is use the stoichiometric ratio, the ratio in the chemical balanced equation. Got my words jumbled. Okay, so our Na2CO3, the 2 things we care about, Na2CO3. That goes on the bottom, so the units cancel. The 2HNO3 goes on the top. Boom, chemical cancels. We're multiplying by 2. We need twice as much nitric acid as we do sodium carbonate. So 0.0077112 moles HNO3. We've got moles. We want to get to volume. We have molarity. So the 0.150 molar, remember, molar is moles over liters. We have moles. We have moles. We want to get rid of moles. We divide by molarity. So the moles part of the molarity goes on the bottom. The liters goes on the top. You could also rearrange our equation if you wanted to. So we're dividing 0.150 moles. Liters flips to the top. 0.051408 liters HNO3, which would turn into 51.4 milliliters HNO3. We multiply by 1,000 to get it back. Questions? Cool. Let's say that we've got this reaction. What's the limiting reactant if you mix equal volumes of 1 molar solution of A and 1 molar solution of B? Which one runs out first? A runs out first. Why does A run out first? A runs out first because we got a coefficient of 2. So if we're using the same concentration and the same volumes, that means we're using the same number of moles. Same molarity and same volume means same number of moles. So if we instead said 1 mole A, 1 mole B, this 2 coefficient in front of A means we're using up A twice as fast, so we would not be able to make as much C. We'd use up all of our A and we'd still have half a mole of B left. The coefficient means that we use it up faster. Questions about any of this stuff so far? Okay. We've got some different types of aqueous solutions. We also want to talk a little bit more about solubility. So consider 2 solutions you're probably familiar with. Salt water, like seawater. Salt water is a homogeneous mixture of sodium chloride and H2O. And sugar water, like often shows up in almost every drink. Not every drink, but many drinks. Sugar water is a homogeneous mixture of sugar and water. With both of these, when you add the salt, when you add the sugar, you stir them, and the solid seems to dissolve and disappear. But how do they dissolve and disappear? That's what sets them apart. So when a solute dissolves, what's happening is that we're separating the units. Whatever our smallest unit of that thing is, it's getting pulled apart. So when a solid solute is placed in a liquid solvent, we get competitive forces. There's interactions between the solvent, like our water, and our solute. There's also interactions between the solute and the solute. Sometimes the solvent-solute interaction is stronger than the solute-solute interaction, and that results in the solute, the solid, getting pulled apart. So the individual pieces get pulled apart by the solvent molecules. That's not always true. Sometimes the solute has a really strong affinity for itself, and it can't be pulled apart by the water. And so in those cases, it doesn't dissolve. So strong solute-solvent interactions lead to dissolving. The solid dissolves. If we have a stronger solute-solute interaction, it's not going to dissolve. The solute says, no, thank you, I'm not interested in what you have to sell me. We're fine here by ourselves. Go away, please. One of the ways that this happens, one of the forces at play with these solvent-solute interactions has to do with the charge distribution in a water molecule. So you may remember from Chem 20 or high school chemistry that electrons are not evenly shared within a water molecule. We're not going to be talking about this in depth, I think, today, but we will cover it more in the future. But the end result of this is that we have a partial negative, partial charge on the oxygen side. Blue? So that's our oxygen. And our hydrogens are kind of being bullied. They're getting their electrons stolen by the oxygen. And so they end up with a partial positive charge. They don't have as many electrons as they should, and so they end up with a partial positive charge. So with a sodium chloride solution, what's happening is the sodium chloride into water, and sodium chloride is an ionic compound. Ionic compounds are positive and negative charges repeating in 3 dimensions, whatever that structure looks like, for as far as we can imagine. Since it's positive and negative charges, the water comes along with its positive and negative charges, partial positive, partial negative charges, and you get little magnet interactions. So it's like we've got a bunch of little magnetic balls, and we're bringing along other magnets and pulling those little magnet balls away from each other. So for the sodium, which is positively charged, the oxygen comes along, latches on, and then because there's so many other water molecules around and they're jittering and moving, it rips that sodium off, and then more water molecules come in and fill its place. And the chloride side, it's the hydrogen side of the water molecules, and those get pulled off and separated. So the Na and Cl are separated. So it's no longer the same chemical structure as it was before we dissolved it. It's getting pulled apart into its individual ions, its individual pieces, and then those are surrounded by a bunch of water molecules, either with the negative side facing in or with the positive side facing in, depending on the charge of the particle. And that stabilizes the charge in the solution. This also results in a solution with free-moving charged particles, and those can conduct electricity. So we call those free-moving charged particles electrolytes. Like in Gatorade or liquid IV, or other such things that you would use to refresh yourself if you're doing a lot of sweating. So electrolytes are substances that dissolve in water and form a solution that will conduct electricity. Electrolytes are soluble ionic compounds. There's also non-electrolytes. So a non-electrolyte solution does not conduct electricity when it's dissolved in water, and this includes most molecular compounds, like sugar. So the way that sugar dissolves when it's put into water is the sugar molecules are pulled away from other sugar molecules, but they stay intact as whole sugar molecules. They're neutrally charged, and so there's nothing in the solution to do a lot of conducting electricity. Sugar molecules are not charged, or rather are neutral, and don't conduct electricity. So if you were to take some distilled water and add salt to it, you should be able to conduct electricity through the salt solution and power a light bulb with a battery. If you were to do the same thing with distilled water and sugar, you probably wouldn't get much, if any, electricity flowing through the water to complete the circuit to allow a light bulb to light up. And this is what I was talking about with the sugar molecules staying intact. So we've got sugar molecules in here. They're neutrally charged. They don't conduct electricity. They're non-electrolytes. Questions about electrolytes? Cool. We also have acids. So one of the slides just a little bit ago said that most molecular compounds don't conduct electricity. Strong and weak acids are exceptions for those. So acids, remember, are molecular compounds. They ionize to form H plus cations, and there's also anions that can be produced. So when acids go into water, strong acids ionize completely. So for example, HCl, we know it's an acid because it starts with H. If you put this into water, it will completely separate into H plus and Cl minus. So it completely dissociates. Completely separates, because I can't remember how to spell dissociates. Is it one S or is it two S? So it completely separates. HCl is one of these, HBr, HI, HNO3, H2SO4, HClO4, some other examples of strong acids. There are also weak acids. Weak acids, strong refers to completely separating. Weak does not completely separate. Partially ionizes / separates. One of the ways that we symbolize this is with the two-directional arrow. So some of our acetic acid is what this is. It's our acetate plus an H in front. Our acetic acid can go to produce H plus and acetate. That can also go the other direction to reform the acetic acid. It's going both directions at the same time. Some of them are losing, some of them are gaining. But it's not a complete separation. These are analogous to strong and weak electrolytes. Strong and weak electrolytes completely separate or partially separate. So strong electrolytes are anything where you throw it into water and it completely separates. A weak electrolyte, you throw it in and some of it will turn into ions, but not all of it. And the extent depends on the chemical. Here's a look at non-electrolyte weak and strong electrolytes. So in a non-electrolyte solution, we don't have any ions being formed in the water, so it doesn't conduct electricity. We can't complete the circuit. A weak electrolyte solution does produce some ions, so it will conduct electricity a little bit, but not very strongly. And then the strong electrolyte solution produces lots of ions, the maximum amount of ions, and so it conducts electricity a lot better. Which of these aqueous solutions, if you had to guess, conducts electricity? We've got KBr, an ionic compound. We've got C6H12O6, which is a sugar. We've got CH3OH, which is methanol. Any guessers? A. A because it's ionic, and also because potassium is very soluble in water, and so that's going to completely separate into its component ions. The other two are not going to ionize much, if at all. For solubility, we can often talk about it in the very most basic terms of is it soluble or is it not soluble? So many ionic compounds dissolve in water, not all ionic compounds dissolve in water. We can either call it soluble if it dissolves in water or insoluble if it does not. Insoluble often means not very soluble. So it may be soluble, but only to a very small extent. And I don't think that we're going to be talking about the extent of solubility too much in this class, but you'll learn all about that in Chem 2. So it might be slightly soluble. When ionic compounds do dissolve, when they are soluble in water, the anions and the cations get completely separated from each other. For example, sodium sulfide completely separates into sodium and sulfide. If we've got polyatomic ions in there, the polyatomic ions stay intact. With some minor exceptions. Generally, though, if you see a polyatomic ion in a soluble ionic solution, assume that the polyatomic ion group stays together rather than breaking into sulfur and oxygen. For solubility of salts, salts just meaning ionic compounds. For salts, things like silver nitrate, it forms a small electrolyte solution. A different salt of silver, silver chloride, is almost completely insoluble. How would we know this? We probably wouldn't. You wouldn't be able to tell usually just by looking at it if it's soluble or not soluble until you've had lots of practice with it. Experimentally, people have determined this. So they've dissolved silver nitrate and they've put silver chloride in water and it doesn't dissolve. How we can tell whether a salt will dissolve or not is either with experiments or with a solubility table. So we will often use a solubility table. There are a couple of ions that will almost always be soluble or almost never be soluble, and some of those you may have to learn. For your solubility table, though, we've got them on one of the sides of your green sheet. So here's a solubility table. The way that we generally read a solubility table, we've got two sections. At the top section, we've got things that are generally soluble. So if you find one of these ions in your salt, that means it's soluble. We will also have some exceptions. So if we meet one of these exceptions, then it's not soluble. So for example, let's say we've got chlorine or chloride in our salt. It's generally going to be soluble. If we have silver chloride, though, it's not soluble. So AgCl, not soluble because it meets the exception. So soluble unless one of these things. The bottom section is things that are generally insoluble or not soluble, or very lightly soluble. So generally, if you've got a hydroxide or a sulfide, carbonates, phosphates, those are generally going to be insoluble unless they're paired with these. So insoluble, if it meets one of these exceptions, then it would be soluble. And we'll do some examples of looking through those. So we want to predict whether these compounds are soluble or insoluble, and then we'll have some time for questions. So NIS, if we look at our green sheet, hopefully you have your green sheet handy. Most of us don't have our green sheet handy. So NIS, typically you're not going to find metals on there, or not a lot of the metals. So we find S2 minus. S2 minus is generally insoluble, except do we have nickel in our exceptions? We don't have nickel in our exceptions, and so this is insoluble. S2 minus is insoluble, and there's not a nickel 2 plus exception, which means that it's still insoluble. For Mg3PO42, we've got phosphate, PO4 3 minus, sorry, are generally insoluble. Do we have an exception for magnesium? No, no exception for magnesium. PO4 3 minus is insoluble. No Mg2 plus exception. We've got then Li2CO3, so lithium carbonate. We find lithium in the generally soluble category with no exceptions. We also find carbonate in the generally insoluble category, but it has an exception for lithium. So that means that this is soluble. So Li plus is soluble, no exceptions. CO3 2 minus insoluble, but an exception for lithium, which is always soluble. And then last but not least, we've got ammonium chloride, NH4Cl. NH4 is ammonium with a 1 plus charge, no exceptions to its solubility. So ammonium chloride will also be soluble. Questions on how we're doing that, reading those solubility tables? Generally, you'll just want to either have your green sheet solubility table, one from the book, or you could also probably find one online that looks about the same. Okay, so part of the reason that we cover solubility, we talk about solubility, is to talk about precipitation reactions. So our water around here is hard water. It's got a lot of dissolved ions in it, like calcium and magnesium. Those can react with things like soap to form soap scum on the side of your bathtub or in your shower. Laundry detergents typically contain sodium carbonate that can form insoluble calcium carbonate and magnesium carbonate, and that can precipitate them in solution. So it has some water softening agents. That's all water softening agents are. They pull out these hard water ions like calcium and magnesium. It pulls them out as a solid, which we call a precipitate. So precipitation reactions, our definition. A solid forms when we mix two solutions or more. So two solutions mix and form a solid. The solid is the precipitate. So a precipitate is something that comes out of solution, often by a precipitation reaction. So a visual example of this, if we've got a potassium iodide solution mixed with a lead 2 nitrate solution, the iodide and the lead find each other, and lead iodide has a really strong affinity for itself, and so it turns into this yellow lead iodide solid in solution. You can also get precipitates other ways by messing around with solubility. But we wouldn't consider those precipitation reactions typically. The way that we predict precipitation reactions is we would take our original components. So we've got potassium iodide, K plus and I minus, and we've got lead 2 plus and NO3 minus. And we're looking for what are the new combinations that we can make. The new combinations are if we take our positively charged ion from one solution and our negatively charged ion from the other solution, K plus and NO3 minus. So we can make KNO3. And our other set of ions are lead 2 plus and our iodide to make PbI2. Those are our two new possible products. To check if those are actual products, we would consult a solubility table. So we'd look and see, is KNO3 soluble or insoluble? We would find that it's soluble. And then we would check our other one, our lead 2 iodide. And we would find that it's insoluble. And since it's insoluble, a reaction occurs. There are some instances where you'll look at 2 different solutions, you'll mix them together. Both of the compounds that you could possibly form are still soluble, so it's no reaction. All you've done is mix 2 solutions together. Nothing fun happens. So the key to predicting these is that only insoluble compounds form precipitates, and I think we have got examples of this coming up soon. Okay, so some rules, some steps to follow. We want to write our formulas for our 2 reactants. Whatever those 2 formulas are. Below that, we'll separate them. I usually will separate them into their constituent ions. So we'll have one set of ions from our first solution, one set of ions from our second solution. And then you swap the negatively charged ions or the positively charged ions, don't swap both. And then put those back together, and those are our products. So that's how we predict our products. Then we would refer to our solubility rules and see if any of them are insoluble. If they're all soluble, we write no reaction. If some of them are insoluble, then we would write an S behind that, and AQ would go behind anything that's soluble. And then our last step is that we would balance the equation. So let's look at what these steps look like in practice. We want to write precipitation reaction when ammonium chloride and iron 3 nitrate mix. So again, we're tapping into our nomenclature knowledge. Ammonium nitrate, iron 3 or ferric nitrate, sorry, ammonium chloride. So starting off, we need to write our reactants. Ammonium chloride is 1. And iron 3 nitrate. Nitrate is NO3 minus. It's got a 1 minus charge. Iron 3 has a 3 plus charge. So we're going to have 3 nitrates. And these are aqueous. We can separate those into their component ions so that we can swap them. NH4 plus, Cl minus, Fe3 plus, NO3 minus. And we're going to swap the negatively charged ions and rewrite them. So the pairings that we're going to have is the ammonium, NH4 plus, will go with the NO3 minus. And then we can combine that to form one of our possible products. It would be ammonium nitrate. They just combine in a 1-to-1 ratio. Our other set would be the iron 3 plus and the Cl minus. When we combine those, we get FeCl3. Either swap and drop or just doing some mental math. So that's what I think was steps 1 and 2 on the previous slide. And then we've got to refer to our solubility rules. So we're going to look up ammonium and nitrate. Ammonium is soluble. So this one's soluble. We'll just put an AQ behind it in case the other one's insoluble. And then for our iron 3 chloride, we're going to find chloride. Chloride's generally soluble except with some things that are not iron 2. So this one's also soluble. So there's no reaction. Which is maybe a little bit of a bummer, because why do we go through all that work of swapping things around and rewriting them? However, we don't have to balance the equation now, so that's cool. Questions about the process there? Almost there. Almost there. Okay, so we want to write the equation for the precipitation reaction that occurs, if any, when sodium hydroxide and copper 2 bromide mix. So sodium hydroxide, sodium, and our hydroxide is OH. Those combine in a 1-to-1 because it's 1 plus and 1 minus. And we've got copper 2 bromide. Copper is Cu. It's got a 2 plus. Bromide's got a 1 minus. So it's CuBr2. Separating those out into their ions. Alternatively, you can just, if you can do the math and like the rearranging to just swap them and go straight to the products, awesome, go for it, do it. For everyone else, we'll separate them out. And then we swap our negatively charged ions. So we've got Na plus, Br minus. We've got Cu2 plus. You've got OH minus. And we combine these. Maybe do a little swap and drop. Get NaBr. We get CuOH2. Copper 2 hydroxide. Questions? Okay, so now we have to look at, are they soluble? So we look up for sodium bromide. On our solubility table, sodium shows up in our generally soluble. We don't have an exception for sodium, so this one is soluble. And then we've got our copper 2 hydroxide. We're not going to find copper on our solubility table, but we find hydroxide. So on our green sheet, if you look on the bottom part, in the bottom of the generally insoluble, we find hydroxide. And there's not an exception for copper. So this one is insoluble. So hydroxide, generally insoluble, no exception for copper 2 plus. So that one's insoluble. So we've got ourselves a reaction, and now we get to balance it. Yay! So we balance it, and now it's balanced. The balancing part, our bromides aren't equal, so we add a 2 in front of our sodium bromide to get those equal. Then we have to balance the Na, so we add a 2 in front of our sodium hydroxide, and then that changes the OH, and our OH we already have 2 on the right side, so those are equal. And we also have 1 copper on both sides, so those are equal. I don't expect you to be able to do it that fast. Just, I expect you to be able to do it, at least with some practice. All right, now what we've been waiting for. There are a couple of ways that we can represent aqueous reactions. We've got a couple types of writing, couple types of ways that we can write out the reactions. One, write out molecular equation. That's what we've been doing. We've only written molecular equations up until now. Molecular equations show the complete neutral formulas. So it's neutral, combined. So our KOH is aqueous. We're writing it together and saying that it's aqueous. What the aqueous means is that it's actually dissolved, and since it's ionic, that means that the positively charged ions are separated from the negatively charged ions. Same thing for our magnesium nitrate. Same thing for our potassium nitrate. So we're showing them with all of the positive and negative ions paired up, even though the dissolved substances are present as ions. Then we've got two types of ionic equations. One of our types of ionic equations is the complete ionic equation. Complete meaning show everything. So all of the ions that are in solution we're going to show, and the ionic part is separate ions. So we're showing what everything is actually like in solution. So anything that's got AQ behind it, we're separating that into the positive and negative. Subscripts would turn into coefficients. Coefficients would stay as coefficients. And then the reason that we do this at all, the net ionic equation. So net means only the important stuff, or remove some stuff. Remove stuff that doesn't react is the stuff that we're removing. You could also think of the complete ionic equation as the gross ionic equation, in the same way that gross pay and net pay, if any of us are workers. Gross pay is the amount that is on paper, this is what you're getting paid, and net pay is after all the taxes are taken out. So our net ionic equation, after all the stuff that doesn't matter that you don't get to actually keep, gets taken out. So our net ionic equation is just going to be showing the things that change. Okay, so we will write strong electrolytes as ions, incomplete ionic equations. Insoluble things, weak electrolytes, non-electrolytes, get written in as molecules. So if it's not soluble, we write it in full equation, don't separate it into ions. Solids, liquids, and gases are also included in that. So for example, this molecular equation our molecular equation shows everything in its neutral form, no ions. To break this down into a complete ionic equation, we've got three things that have AQ on them, and so we're going to separate those out for our complete ionic equation. And since we've got two of the NO3 minuses, we put a 2 in front of it. We've got our KCl. Our KCl gets separated into K plus and Cl minus, and they both get the 2. So 2 K pluses, 2 Cl minuses. The PbCl2, because it's a solid, stays together. We don't separate it out. Anything that's solid, liquid, or gas stays together. And then our KNO3 here at the end also gets separated out into K plus and NO3 minus. So anything that's AQ, separate it out into its ions. That gets us our complete ionic equation. Typically, we're going to do a complete ionic equation before we do a net ionic equation. Questions about equations so far? Okay, so to get to our net ionic equation, we need to remove some stuff. Our complete ionic equation includes some ions that we would call spectator ions. Spectator ions, just watch. Similar to spectators at a sporting event, if you remove all of the spectators, the people can still play the sport, as we saw a few years ago. Right? You can take all the fans out of the stadium and the athletes can still play the game. It's not as exciting, it's not as fun, but they're not the important part. The fans aren't the important part of the sporting match. So the spectator ions, the way that we can identify spectator ions is they didn't do anything. So for example, our nitrate, our potassium, we have them on the left side as ions, we have them on the right side as ions. Nothing changed about them. So we can just get rid of them. And that's what we do to get our net ionic equation. So get rid of the K plus, the NO3 minus, and all that's left is the stuff that reacted. So we've only got the stuff that reacted. And that's our net ionic equation. The other way you could do this, instead of removing spectator ions, you could just say, I'm only going to write this stuff that turned into a solid at the end. That would also be valid. Okay, and we'll do one example. Consider the following reaction occurring in aqueous solution. We want to write the complete ionic equation and the net ionic equation for this reaction. Okay, so everything that's got AQ is going to get separated into its ions. So HI gets separated into 2H plus and 2I minus. I'm omitting all the AQs that is going to go behind almost everything because I just don't want to write it out. Moving on to our next aqueous thing, we've got barium hydroxide. We've got one barium. Barium's going to have a 2 plus charge on it. And we've got a subscript of 2 following our hydroxide. So we're going to have 2 OH minuses. And that's everything on the left side or the reactant side. So we write in our arrow. And then next up is our 2H2O. This is a liquid, so we just write it in as 2H2O with the L after it to let us know that it's liquid. Then we get to another aqueous product, because this is an aqueous product. So we've got barium 2 plus, and we've got a subscript of 2 on our iodide, so we've got 2 I minus. So this is our complete ionic equation. Everything that's actually as an ion in solution, we've separated out to show as an ion in solution. Now let's identify some spectators. What's something that doesn't change from the reactant side, the left side, to the right side, the product side? The barium, right? We've got Ba2 plus on the left side. We've also got it on the right side. What's our other spectator ion? The other spectator ion is the I minus. So we're going to remove the things that are underlined, the I2, so the I minus and the Ba2 plus. And we'll rewrite it with just the things that are left, and that's our net ionic equation. So we've got 2H plus 2 OH minus goes to 2H2O liquid. Questions at all? Okay, then we will stop there and pick up on Thursday with possibly the rest of the chapter.